We are looking at a paper called Single minus-gluon tree. Amplitudes are non-zero.
Yep. The authors are a team from places like Harvard, Cambridge, OpenAI, Alfredo Guevara, Andrew Strominger, a real who's who.
Okay, so here's the 1-minute summary for everyone. For about 40 years, physics has assumed that something called single minus-gluon tree amplitudes were always zero, just nothing.
A settled fact.
This paper proves that's not true. They are, in fact, non-vanishing in these very specific half-collinear setups you can find in Klein space or with complex momenta.
And for this audience, here's the real kicker.
This is the headline. The key formula for this amplitude was actually conjectured by GPT 5.2 Pro.
And then proved by another new internal OpenAI model. It's this piecewise-constant formula that, amazingly, satisfies all the physics rules, like Weinberg's soft theorem.
So it suggests AI is graduating from just being a fancy calculator to, well, a symbolic co-theorist.
It's a huge result. I mean, you have a fundamental assumption in quantum field theory just overturned. And the tool that found the crack in the wall was an LLM. It saw a pattern humans couldn't.
So it's a physics breakthrough and an AI breakthrough all in one. Let's start with the physics to, set the stage. Why did everyone think this single minus thing was zero in the first place?
Right.
And maybe give us a quick refresher on what a scattering amplitude even is for those of us who spend more time with transformers than colliders.
Sure. So in the simplest terms, a scattering amplitude is just a function. It encodes the probability of an interaction. You smash particles together, say gluons.
And you want to know what's likely to come out the other side.
Exactly. The amplitude is the complex number you have to, you square it to get that probability.
We used to calculate these with Feynman diagrams, right? Little stick figures.
Historically, yes. You draw every single possible way the particles could interact. You assign math to the lines and the vertices, and then you sum it all up.
But the problem is the combinatorial explosion.
Oh, it's a nightmare. You add one more particle, and the number of diagrams just blows up. It grows faster than factorially, becomes impossible to compute almost immediately.
I've heard this called the simplicity phenomenon. You do all this math, pages and pages of it, and then thousands of terms just cancel out, leaving this tiny, elegant answer.
Precisely. And that massive cancellation tells you that Feynman diagrams are, frankly, a terrible way to describe what's really going on.
Nature knows a shortcut.
Nature isn't doing the algebra, yeah. A great example is the Park-Taylor formula from the 80s. They looked at a specific setup called MHV, maximally helicity violating.
Helicity is basically the particle's spin, right?
Right, plus or minus spin relative to its direction of motion. So Park and Taylor found that if you have exactly 2 minus helicity particles and any number of plus particles, the whole messy amplitude collapses into one single beautiful term.
Okay, so 2 minus particles gets you a simple formula.
But the dogma was that if you went one step further, if you had only 1 minus particle, the amplitude was just 0. End of story.
Nothing to see here, move along.
That was the assumption for decades, yeah. The mathematical argument for it is based on the polarization vectors of the particles being orthogonal to each other. Okay. The math basically says the minus vector and the plus vectors just don't overlap in a way that allows for an interaction. So the product is 0.
But this paper finds a loophole. It's not always 0.
Exactly. They found the argument completely fails if the kinematics, the way the particles are moving, are in a very specific state they call half-collinear.
Half-collinear. That sounds like a geometry edge case. What does that actually mean?
To get this, we have to talk about the coordinates they use. In modern physics, we don't really use standard momentum vectors. We use something called spinor helicity variables.
You see them in the paper as angle brackets and square brackets?
Right, I and IJ. Now, normally, if two particles are collinear moving in the same direction, both the angle brackets and the square brackets go to 0.
Makes sense.
Half-collinear is this bizarre state where all the angle brackets are 0, but the square brackets are not 0.
Wait, how's that possible? If we're moving in the same direction, shouldn't all our relative coordinates vanish? How can one set be 0 and the other not?
In our universe, you're right. We live in Minkowski space. And in Minkowski space, those angle and square brackets are complex conjugates. If one is 0, the other has to be 0.
So this half-collinear thing is impossible in the real world.
It's impossible in our signature of space-time, yes. But theoretical physicists love to play in different mathematical sandboxes. They move to what's called Klein space.
That's the one with 2 time dimensions and 2 space dimensions, the 2 TSD signature.
That's the one. Or you can just treat the momenta as independent complex numbers. In that space, the angle and square brackets are independent. You can force one to 0 while leaving the other alone.
So they looked in this mathematical crack in reality.
And in that crack, in that half-collinear region, the single minus amplitude is suddenly not zero.
And finding that was important, but actually calculating it was the real challenge.
Oh, a total nightmare. You can't use Feynman diagrams. They used a method called Berends-Giele recursion.
For our listeners from the ML world, is that anything like a recurrent neural network?
It is recursive, yeah. It's conceptually similar. You build up the amplitude particle by particle, you calculate the interaction for, say, 2 particles, and then you reuse that result as a building block to calculate for 3, and so on.
So you're recycling the computation.
Very efficiently. And when they applied this recursion in Klein space, they found the amplitude has this fascinating property. It's piecewise-constant.
Meaning it's not a smooth curve, it jumps.
Exactly. The space of all possible momenta is tiled like a floor. Inside each tile or chamber, the amplitude is just a constant integer, a whole number. But when you cross from one tile to another across a wall, the value just jumps.
So it's like a map of integers. +1, -1, 0, maybe +2.
Yes. But here's the problem. Figuring out which integer goes in which chamber for any number of particles is insanely hard. The combinatorics just explode again.
And this is where the human researchers got stuck. They knew it wasn't 0, but they couldn't find the general formula.
They were stuck on a specific, simplified part of the problem they call region R1.
Let's define that. What is region R1?
So R1 is a specific slice of that half-collinear world. It's a setup where you can find a frame of reference where one particle number 1 has negative energy and all the others have positive energy.
Okay, so particle 1 is the odd one out.
Yep. Geometrically, particle 1 is on one side of a line through the origin and all the others are on the other side. In this region, the recursion simplifies a bit, but you're still left with this enormous sum over ordered partitions.
That sounds like a computer science problem.
It is. You have to sum over all the ways to split a list of particles into groups. For just 6 particles, you've got 32 terms. For 7, 8. It grows incredibly fast. They had the data points for low numbers, but they couldn't spot the pattern.
They had the training data, but they couldn't find the function.
Precisely. So they did what you do now. They fed the data, the recursive definition, everything into GPT 5.2 Pro.
They just gave it the sequence and asked, what's the closed form expression?
That's the gist of it. And the model came back with a conjecture. It's equation 39 in the paper. It suggested that in this whole complicated region, the answer is just a signed product of projection operators.
Okay, can you simplify that for us?
It means the answer is always just +1, -1, or 0.
That's shocking. You have this huge explosion of terms, and it all just collapses down to a single bit of information. Positive or negative?
That's the discovery. The AI saw through all the algebraic noise and basically said, hey, this looks like just an alternating sine function.
Okay, but I have to be the skeptic. LLMs hallucinate. Even this one. It's a probabilistic model. Just because it guesses a formula doesn't make it physics.
You're absolutely right. A conjecture isn't a proof. And this is where the workflow gets really interesting. The paper says the conjecture was then proved by a new internal open AI model.
So one AI guesses the answer, and a second AI provides the rigorous proof.
That seems to be what happened. We're getting into the era of automated theorem proving, but, and this is so important for the science, the humans didn't just trust the black box, they verified it themselves.
They checked the math by hand.
They checked it against the recursion for more particles. But more importantly, they checked if this simple little formula actually obeyed the fundamental laws of physics.
This is the real test. Does the AI's answer behave like a real gluon?
Exactly, and they put it through the ringer. First step is cyclicity. An amplitude for particles A1 to n has to equal A to n1. The physics can't depend on where you start counting in the circle.
And the AI's simple formula of pluses and minuses passed that.
It did, which is not at all obvious just from looking at the formula. It also passed reflection symmetry and some other constraints called the Klein-Keif relations.
What about the big one? I know Weinberg's soft theorem is usually the final boss for these kinds of claims.
It's the gold standard, absolutely. Steven Weinberg proved that if you take the momentum of one gluon and you shrink it to 0, make it soft, the amplitude has to behave in a very specific, predictable way.
So if the AI had just found a random pattern that fit the training data, it would almost certainly fail this test.
100%. The soft theorem is a deep physical constraint, and the AI's conjectured formula satisfied Weinberg's soft limit perfectly.
That's just wild. The AI wasn't taught Weinberg's theorem, was it? It was just looking at the symbols.
That's the core insight here. It found a pattern in the math. The fact that this pattern also obeys these deep physical laws means the AI found the underlying truth. It didn't just overfit the data, it found the actual generating function.
Okay, so we have a formula, it works, it proves single minus amplitudes aren't zero. Why does this matter? What does this unlock for physics?
It ties into some really big, really current areas of theory. The main one is something called self-dual Yang-Mills, or SDYM.
Break that down for us.
It's a special sector of the theory of the strong nuclear force. And there's been this long-standing tension. The classical solutions of SDYM are known to be incredibly rich and complex, but the quantum side, the tree-level amplitudes, were thought to be almost entirely trivial. Mostly zero.
So you had this complex classical world, but an empty quantum one. A mismatch.
A huge mismatch. You want your quantum theory to build up to the classical one. These new non-zero amplitudes are the missing link. They populate that quantum desert. They provide the non-trivial structure you need to match the classical theory.
So it fixes a long-standing puzzle.
It seems to, yes. And there's also a big connection to celestial holography.
Okay, that sounds like something from science fiction.
It's a very cutting-edge approach to quantum gravity. The idea is that the physics of our four-dimensional universe can be described by a simpler theory living on a two-dimensional surface at infinity.
And since we're in Klein space...
Exactly. The boundary at infinity isn't a sphere, it's a torus, a donut shape. And the paper shows that if you do a certain mathematical transformation of these new amplitudes, you get known functions that live on that celestial torus.
So this gives those researchers new data points to work with.
It gives them a precise dictionary. Here's the 4D gluon thing, and here's its 2D counterpart on the torus. It helps validate their entire program.
And the paper says this isn't just for gluons, it works for other particles too.
It generalizes, yeah. They say the method works for gravitons, the particles of gravity, and it also has a simple path to including supersymmetry.
So this is a general feature of how these theories are built, not just a weird quirk of gluons.
It seems to be. And it validates this whole methodology. Go to a weird complex spacetime, generate data using recursion, have an AI find the symbolic pattern, and then check if that pattern obeys the laws of physics.
I want to go back to that simplicity phenomenon we started with. The paper ends by saying that even though their formula is a huge simplification, they think an even simpler one might exist.
That's the really tantalizing part. They hint that if you could just find the right set of variables to describe the problem, something even better than spinors, this whole thing might collapse even further.
We're always chasing the source code, hoping it's written in just a few elegant lines.
And for 40 years, we thought the line of code for single minus gluons was just return zero?
When it was actually more like an if statement. If half-collinear, then do something else.
Exactly.
It really makes you wonder what other things we've just assumed are zero.
That is the big takeaway for me. In physics, zero is such a strong statement. It usually means there's a deep symmetry, a law that forbids something from happening. But sometimes. Sometimes zero is just because we haven't looked in the right place.
Or the right cracks in the kinematics.
The half-collinear regime is a very specific crack. But that's where all this new, rich structure was hiding.
This changes the image of scientific discovery. It's not just a lone genius at a blackboard anymore. It's a team of geniuses asking an AI to solve a problem that was just too tedious to do by hand.
And that collaboration is letting us map out these dark corners of the mathematical landscape of physics that were just inaccessible before.
So here's a final thought for you to chew on. If an AI model can guess a formula that satisfies something as deep as Weinberg's soft theorem just by looking at data, what other impossible things in physics are actually possible? What other zeros are just waiting for us to ask an AI the right question?
We could be surrounded by hidden structures we've just defined away as being empty.
And that is a fantastic and slightly unsettling place to leave it. We'll put a link to the paper in the show notes if you want to brave the Klein space math for yourself.
Good luck with all the indices.
Thanks for listening to this deep dive at the intersection of AI and fundamental physics. We'll catch you on the next one.